good time as well. Okay, then I guess we'll start with the talk. So this talk is about Python and IoT, and I called it From Chips and Bits to Data Science. So we'll start at the hardware level and work our way up. And I'm Jeff Fischer. I'm currently an independent consultant and doing some work for a research lab in Sunnyvale. And if you go to this website, I have all the slides and everything available if you want to play around with this afterwards. And if anyone actually tries any of this stuff out, I'd love to have you email me. I'd like to hear what you do. This was a hobby project for me, but it was a lot of fun and I learned a lot of stuff. So I'd like to help out if anyone has questions, if they try it out. Because I can't obviously give every little detail of how the thing works in one talk. But all the code's up there on GitHub. So, okay, so I'm going to give you an overview of what the project I did was, and then kind of go into each area, which is hardware, capturing data, doing data analysis, the actual light player, and then some parting thoughts. So the motivation, well, the real motivation is I wanted to learn about IoT. I was coming off of a startup, and I wanted to do something different, and I heard that this IoT thing was cool. And there's a lot of interesting trends about, have very low power chips that have Wi-Fi and Bluetooth built in, and you can throw them all over the place and do interesting things with them, and they can talk up to the cloud, and there's analytics in the cloud. So I think there's some real trends behind this IoT thing. It's not just hype. I think there's something there. There's also a lot of hype too. But anyway, so I thought, it would be cool to do something, and I'd like something that involves sensors, not necessarily robotics, but something that was involving sensors, real data that's noisy and has problems with it. So it's not just some theoretical thing. And I wanted it to control something as well. And I thought about maybe like control the furnace or whatever, but I don't want to necessarily break my furnace either. So I said, well, what else can I do? How about controlling lights? And I found there's these Phillips makes these smart lights. They're a bit more expensive than a regular light. But what you can do, you just screw it in the regular light socket, and it's all wireless. There's no wiring changes you have to make or anything. So it's really easy. Yes, the Hue. And sure, is it the Phillips Hue lights, H-U-E? That's the thing. And there's some more detail later in this slide deck. So anyway, but there's some problems. So the problem I ended up solving, this is actually my wife's idea, was you go out of town for the weekend. We have 2 kids. We go on these road trips for the weekend. We have a house. We don't want to leave it all dark because then someone might go and steal all of our electronics or something, right? I mean, Sunnyvale's a pretty nice neighborhood, but it can happen. So you don't want to leave an invitation. So you can put on timers on the lights and things like that. But we always last minute we're trying to figure out how to set the timer, and you're not sure if it's actually going to go on or not, and they're flaky, and they're also very predictable. So if anyone was really watching the house, they go at 7 o'clock it goes on, at 9 o'clock it goes off. Wonder what that is. So anyway, so we'd like something. So I was thinking, how about something that'll automatically play the lights at random, right, using these smart light technology, right? And like a self-contained solution, I don't want to involve the cloud and all that. You've probably heard about all the big denial of a service attack that was using these IoT cameras, right? And so I wanted something that will actually only be contained within my network. And it would be also cool to use machine learning. So that's how this came up. So this is sort of the kind of how the project works. It's actually 3 separate phases. First, there's what's called Lux Sensor. So Lux is a measurement of the light level, and it's an SI unit apparently. So if you see that, basically, if you see me using the word Lux, I'm talking about light level. So there's some light sensors, and there's a data capture phase where I basically run this thing for a month in my house and capture light levels in different rooms so I know what the standard patterns are. And then what I do is the second phase is basically doing a bunch of analysis and machine learning to understand what these patterns are and come up with some algorithm that can play back something that looks like the real patterns but is randomly generated and varies every day. And I wanted to account for things like sometimes you get up at the same time every day and go to bed at the same time, but you also have like sunrise and sunset are varying as the seasons progress, right? And so that can impact, your usage of lights. And if it's, and if I set it up in the summer and everything's fine, then in the wintertime, it might be that no lights are on for the first 2 hours because it's dark, whereas in the summer it was light. So I want to make it smart enough to handle those kinds of things. Okay, so then the last phase is the actual player application. So this takes the stuff that came out of the machine learning and plays it. There is a little more detail of how I set these 3 pieces up. So I have basically 3 sensors in my house, and 2 of them are using this chip called the Esp8266. I know that's a mouthful. That's, electrical engineering people like to have these numbers for all their chips and all. And if you can see it, I'll show a picture in a minute, but this is the actual size. And the board that for this is $15, and I think you can get like cheaper ones for like $5 off of distributors in China and stuff like this. But and it's very small. It's got 96 kilobytes of data memory. That's not megabytes. That's not gigabytes. That's kilobytes. And it's running Python. It's running a version of Python called Micropython, and it's running it on the bare metal. There is no operating system on that thing. So, but the cool thing is, since it uses low power, you can have a battery, and it has Wi-Fi built into the chip. And so you can put these around the house, have sensors, and even control whatever you want. And you don't have to change your wiring, and you can gather data. So really, really convenient. And fun to play with, running Python on the bare metal is fun, I think. Anyway, so then I have my big server. I have a massive server. My big server is a Raspberry Pi. And and the funny thing is when you start working with these things and you get out of memory errors, and you have to kind of like crunch your program down and take all the comments out so that it'll actually parse. And then when you go to this thing and it's running Linux, you go, wow, this is a big environment here. It's really funny. So I'm using this protocol called Mqtt. It's a message queuing protocol that's common in Internet of Things. And there's a Python client to it, and you can get on Linux. There's a server. I think it came out of Eclipse project. So I'm running that, and that's what the communication is doing. And then on here, it has its own sensor, because when I first was playing with this, I stuck a sensor on the Raspberry Pi, so I get one for free then. And so then there's a data capture app that's capturing the data, and I'm writing the data to flat files. So just CSV, the spreadsheet format.
Question, Jeff.
Yes?
The Esp8266 talks to your Pi via Bluetooth or Wi-Fi?
Wi-Fi. So it has,
Bluetooth, right?
no, I think they have, so the company has a newer one out. It might have Bluetooth as well, I'm not sure. But this chip only has Wi-Fi, no Bluetooth. Oh, for the Pi, it's okay. For the Pi, so it's talking to the network via Wi-Fi. The Raspberry Pi, I'm actually using Ethernet. So I have a Raspberry Pi 2. It doesn't have any Wi-Fi on it. I have a Wi-Fi dongle, but it's just because that's where our dining room is my server room, and it has all this hardware that came out of my startup you wouldn't believe. Sitting in there, Mark over there knows I have a UPS. I can run like all kinds. It's kind of funny, but anyway. So, but this thing I have is just plugged into my Ethernet network, my network via Ethernet, and but these things are just using the Wi-Fi then. What's the what? Power. So I don't know. I think it's like a couple hundred milliamps. So this is a 350 milliamp battery. So this is the power supply. It also runs off of, you can drive it off of the USB as well. But that's the power supply.
Can it be powered by the Ethernet itself? Some of the stuff too.
Oh, that doesn't have so that one doesn't have an Ethernet connection. It just has Bluetooth, so you can power it off of Bluetooth. Okay. I have some pictures that it'll be clearer in a few slides. So this is the data analysis phase. And for this, because my Raspberry Pi it's headless, it doesn't have any monitor hooked up to it. I don't have a GUI on it or anything. So I just copied the files off and used my laptop and did all the data analysis on my laptop. And I'm using Jupyter Notebook. It used to be called IPython Notebook. It's horrible trying to type in Jupyter spelled like that. But that apparently stands for Julia, Python, and R, because those are some of the original languages they supported. But it's a great environment because you run it in, it has a little server and it runs in, brings up your browser, and you can type Python and you can graph things and it'll immediately show you the things and you can tweak it. And so that's what I did for the data analysis. And I have some examples later. And so this is the replay application. So I'm using the Raspberry Pi then. So I should mention that the output of this whole thing is some definitions of hidden Markov models. And I'll talk a little bit what that is. But that's the output of this analysis. And then that's used to drive the playing script. And the playing script is like a 200-line Python script that's going to, control these lights. And the way these are Phillips Hue lights, and the way they work is that they have a little bridge that plugs into your network, and you can control the lights then using HTTP, and it has a REST API. And then from there, the lights themselves don't have any special wiring. They're using the Zigbee protocol. And it's kind of invisible to you. You don't have to worry about it. So you just unscrew your old light, screw this new light in, do initial configuration, and then you can control your lights. And there's also like an app that you can do from your iPhone. So like if you want to scare your kids and play with the lights when you're not in the room, things like that. So, yes?
The Hue bridge is also wireless?
I think they do. Mine wasn't, but they probably have a wireless one as well.
So you have it connected, routed by Ethernet?
Yes, yeah. From my dead startup, I have lots of extra Ethernet boxes as well. So, but yeah, I think I don't know if this particular model has it. I'm pretty sure they have a model that'll run off of the Wi-Fi as well. Yes.
It's a good question from your Wi-Fi router. What protocol do you talk to the bridge?
So this just sits as.
Repeat the question.
Yeah, he was asking what protocol we use to talk to the bridge. And so this bridge, this is just a device on your IP network, right? So then it has a little server embedded in it, I believe. And so it has a little web server and it's talking HTTP. And so then you can control it through this REST, whatever, I don't remember what REST stands for anymore, but like web services like API. And then there's actually you don't actually have to talk to HTTP yourself because someone has already gone and written a Python library called Hue, Python Hue, or Foo, something like that. Anyway, they've written a Python library, yeah, that's exactly Hue, that you can use and you can deal with Python objects even. You don't have to deal with the actual requests. So that's a nice thing about using Python for all this. You're looking to do something, you go look and you'll find a Python library to do it. And so that makes it a lot quicker than if you had to write a lot of code yourself. Okay, now I'll go into more detail on the hardware. So one thing I just wanted to mention, so I got started in hardware when I was a kid. I played around with electronics, and back then they had these 40-pin dual inline package chips. There were these things like the Z80, and I did some wire wrapping and all. And of course, the fun thing is when you have like 1,000 wires and there's a loose connection somewhere and nothing works. And so things have changed a lot since then. And I hadn't really touched hardware since then. But so I recommend this site Adafruit. So this is a company, I think they're out of New York City, and it's really focused on the hobbyist who wants to do things with electronics. And they have lots of documentation and examples and things. So like I just was looking there to build this screenshots for this presentation. And just last week, they have a new tutorial on Micropython with the Esp8266, which wasn't there like when I was doing it. Otherwise, it would have been a quicker process. But so they're always coming out with new tutorials, lots of documentation. And they have these things called breakout boards. So what a breakout board is, a lot of the modern chips are on these surface mount semiconductors, and they're really hard for a normal person to work with, right? They're really for large scale manufacturing. What the breakout door does is it puts a couple of those chips on a board and provides easy contacts so you can get to it. So the main chips I'm using are on these breakout boards from Adafruit. And there's a couple other companies that provide them. But I'm really happy with them because they're, anyway, that's my little advertisement for them. So this is kind of the tools I use, and I didn't, because I hadn't touched this stuff since grade school. I had to go out to Fry's and buy all this, but it's not that expensive. I think my wife actually had the multimeter. And we had so what a multimeter is, you can use it. It measures voltage, amps, and resistance. And the main things you're going to use it for is if you want to measure voltage levels to know if you're getting 5 volts or 3 volts or no volts when you think you're getting something. And also continuity with the resistance, you can tell if you have two connections or not. You do need a soldering iron for some of these because Adafruit is masochistic, and they think everyone should learn to solder. So when they give you these breakout boards, the pins on them are not soldered on, so you have to do that yourself. And I know it's anyway, it's not too hard. And so breadboards, these are useful for prototyping electronics. So you just stick the chips in and you can plug the wires in. That's what I did there. You can come take a look later if you're interested. And there's you need wire strippers to pull the insulation off the wires, or you can get these pre-cut wires, wire cutters. So pretty simple, not a lot of fancy equipment. You don't need an oscilloscope or a digital logic analyzer or anything like that. Okay, so this is what my hardware looks like on the Raspberry Pi. Not very pretty, but so this is my Raspberry Pi. It's a Raspberry Pi 2, and there's a GPIO bus is what it's called, and there's a connector there. You can't see it because of this cable. So this cable, what it does is it lets you pull those wires out and then have it be able to connect that into a breadboard and get to it more easily. So that's something I got from Adafruit. And then I have a light sensor. So this is the Lux Sensor chip. It's a breakout board, so there's a chip, and I think it has a voltage regulator and a few other things on it. And for fun, I have an LED that I can turn on and off to. That was kind of my first project before I got up to the light sensor. And the light sensor is using a serial protocol called I2C. And there's software on Linux side as well as in Micropython to talk to that protocol, so you don't have to worry too much about the details. And if you download the slides at the end of the whole deck, there's some wiring diagrams if you really want to try this. Okay, so this is the Esp8266 board. So I put together 2 of these. I got a couple more laying around I still need to put together. But so it has a battery, like I mentioned, so it can be powered from the USB connector or through the battery, and you can charge this board. It is set up so it can charge the battery through the USB, which is convenient. The other thing is the USB acts as a serial connection. So if we have time at the end, I'll show you a demo where I can talk the Python REPL, read, eval, print loop through the USB connection. There's a way to set up a little web server on this and then talk to that through the Wi-Fi. But I kind of thought that was a little bit of a security risk, so I disabled it. Plus, it gives me more memory for my actual application. Let's see. So I guess that's pretty much everything there. I'm using the same light sensor here, and you can see it's only about 5 wires that need to be connected. Yes?
Did you leave it on the breakout board for the finished product, or did you go inside?
This is the finished product. Yeah, I guess the only problem was when I was getting ready for this talk, and I went over to take the picture of the Raspberry Pi, I found that the LED was missing. Because I had gone on a trip to Germany and brought it with me, and somehow when it was in the box, it came off. So I get, probably if I really wanted to be fancy, I should go and solder them up. But as long as you're not hitting it too much, it's okay. Okay, so data capture. So this is just a review what we're doing data capture. We got these things talking over the Wi-Fi and passing it to the queue, and we're gathering the data. So as a part of this project, and I worked with my former PhD advisor and built a framework called AntEvents. And this is a little framework for kind of dealing with event-driven IoT data. And it's only available in Python 3. And it is for it's kind of specialized for IoT processing. And it's using, so in Python 3.4, they have a module called async IO, and it kind of uses that as the main scheduler. And there's also, I also ported it to Micropython, and porting it means basically cutting out 90% of the code, just having the very core API, because it doesn't have enough memory for anything else. But the code looks very similar on kind of the larger system than on the smaller system. And again, the idea is it has this idea of push-style events, and it's kind of a very fine-grained publish-subscribe model, and has some support for stateful filters and uses method chaining that you can connect. Basically, you specify how things are connected, and then tell it to schedule it, and then it'll kind of run everything for you. And can talk to other systems. Anyway, and it's all on GitHub if you're interested. And I spend more time writing the documentation than the code, so hopefully it's understandable. So this is kind of a simple example. So this is an example where I'm reading from a light sensor. I'm going to go through a couple steps where I'm going to extract out a value. I'm going to capture a running average over the last 5 data samples. I'm going to then convert it to either true or false, whether it exceeds some threshold, and turn on an LED. And this is what the code looks like. So I instantiate a sensor. Then from that sensor, I'm basically connecting, I'm basically running these steps. I'm setting these up. And they're not running real time. What happens is it just sets up the configuration, then you pass it to a scheduler. And I say, I want to schedule this light sensor to be sampled once every 2 seconds. And then it'll go off and run and do that. And this is similar. Microsoft has this framework called RX, and they have like an RxPY. It's a very .NET oriented thing, but it has kind of similar ideas. And there's also Link, which is kind of what that was even derived from. So we borrowed some ideas from there, and we extended it a bit as well and simplified it for IoT. So this is the code that I'm running on these ESP8266s. So there isn't much here. One thing I had to do is that the light sensor is not trivial to read it. And there wasn't, at least at the time when I was doing it, there was no code for that. So, but Adafruit had written some C++ code, and then someone had ported it to run in Python on the Raspberry Pi. So I took that code and tweaked it and got it to run on this. So there's a 3rd generation code, but it works. And I have I think now they actually have built-in support for Mqtt. When I wrote this, they didn't. But so there's a little writer there. So all I need to do then is basically I talk to the Wi-Fi, instantiate a sensor and the thing that's going to write to the queue. Then I schedule it every 60 seconds. I'm sampling data, and then I tell it run forever. And so that's what the code looks like then that runs on the thing. And at the end, I'll show a demo if we have time. So the Raspberry Pi data capture code is a little more complicated. So I'll just show a graphical view of that. It's not that bad, but basically I have this light sensor that's sitting on the Pi. So I want to capture those events once a minute and write those to a flat file. I'm running it to CSV files. And I'm also want to read from this queue where the other 2 sensors are sending their data. So this will read from the queue, and it does some mapping steps to convert the data. Say this is the character encoding. It happened to be JSON data, so I decode it and do a few mapping steps. Then I basically dispatch it to one of 2 flat files, or depending on how many nodes I'm getting data from, each one gets its own flat file. So pretty simple. And one of the things is that AntEvents will handle the threading model for you. So all this is running is event-driven code running in the main thread. But these things actually, so Mqtt, there's a separate event loop for that. So we have to run that in a separate thread. And this is running in a separate thread. But all that's handled through AntEvents. Okay, so data analysis. Is there a question? Okay. How are we doing on time here? Okay. So again, for data analysis, what we want to do is we want to take the data. I'm going to pull those flat files off, and I'm going to use Jupyter Notebook to analyze them. So the steps that I'm taking in data analysis more specifically are basically read and preprocess the data file. So I'll go through some steps to kind of smooth out the data and pre-process it. Then it's kind of almost analog data in the sense that it's, it's some floating point number between 0 and 1,000 or something like that. And there's a lot of different values. So I want to convert this to maybe a smaller number of discrete values that I can look at. And then I got to map that to saying, okay, was the light on or off based on those values? And once I have these kind of history of when the light was on or off and these timestamps of these samples, then I can go and train hidden Markov models, and I'll explain that. And then finally, once I've kind of come up with an algorithm for predicting the light, then I want to go look at it and see if it makes sense. And if it looks good, and so you do a lot of the debugging by graphing the data out and taking a look and seeing if the graph is what you expect. And if you get the prediction is the light is off all the time, that's not very useful. And I was getting a lot of that initially. So, and then finally, then I can export these for the player phase. Okay, so I'm running AntEvents in Jupyter. And so this is kind of the sequence of processing steps for the pre-processing. And so the key thing, one of the key steps is that since this is real world data, you have gaps in the data samples. So like when my daughter bumped the Raspberry Pi off the dining table and it was disconnected from the power supply, right, then there's no samples. Or if I'm fooling with something or there's some problem with the Wi-Fi network, right, you get gaps in your data. So what this step did then is I went and looked. I'm expecting a sample once a minute. So I went through, as the samples are coming in, as I'm reading them in from the flat file, then I look for gaps where it's like more than 4 minutes. And if there's a gap of more than 4 minutes, then I insert an extra value. Basically, I give it a timestamp, and then I give it a value of not a number, which is a floating point value. And so that kind of indicates to the downstream code that there's a gap there. And that's used for two things. One thing is all the graphing code that Jupyter has will actually put a gap in the graph, which is what you want. You don't want a line connecting the two dots if there's a big gap in time. And the second thing is when I'm actually analyzing the data, I don't want to treat it as contiguous data. I want to treat it as I have multiple separate data sets that started at one time. Then when I hit the gap, I need to start another data set. So that's what that's for. Then I have these adapter pieces. Basically, I'm using there's a data analysis framework called Pandas, and it has some very convenient functionality for doing graphing and representing things that look kind of like rows and columns and handling timestamp data. So basically this adapter will create a Pandas series data structure, which is, if you've heard of Numpy, it's basically a wrapper over a Numpy array. And so those get created then at the various points here in the data stream. And so one of the things I'm doing, you'll see, is I'm running a sliding mean. I'm basically doing an average of the last 5 values, and that kind of acts as a low-pass filter in electrical engineering terms to filter out kind of some of the high-frequency noise from the signal. And this is what the code looks like in AntEvents. You can see you're basically using method chaining to kind of build up this structure. Okay. So this is like what some of the data look like. This is over like a 3-week period. I was going on a trip, and I was like rushing to get this thing going. I kind of got it going right before I went on the trip. But I knew I wouldn't be able to keep it running during the trip because there was a bug somewhere where the thing with the Esp8266 node would crash like after a day. Eventually, I think I did a firmware upgrade and that went away. So then I basically have this big gap here of 2 weeks, and then you can see then I finished out with another 2 weeks of data, I think, or 1 week or something like that. And you can see there's a very regular pattern to the data. Yes?
What is the y-axis?
So this is the Lux level reading coming out of the sensor. So that's 600 lux, whatever lux is. And 0 is where the light is, the room's completely dark. So this would be bright sunlight or a very bright flashlight shined on it. Because in this front room, I mean, the other thing, obviously in IoT, you're dealing with the real world, and you have to understand what's your environment. So in this room, the sensor was sitting on my desk, and there's a bright lamp there. So you're going to get some light from the lamp, or you might get some light from sunlight. And the lamp light is going to be much brighter because it just so happened the lamp was right there.
So does this break down the granularity by hours?
So this chart is showing you 3 weeks.
Right.
You might be, well, I'll show you in 2 slides. I'll show you for 1 day. It's a little more readable, right? But so this is showing all the, I mean, I don't know if it does, I think it's showing you all the data points then over those 3 weeks for one per minute. So it's graphing a value for every minute over those 3 weeks, except for during this time when there's no value. And so this is showing you the other 2 rooms, so you can see all 3 rooms together. You can see it's a very similar pattern, but not exactly the same, right? And this is showing you for the last 24 hours of the data, so it's a little easier to follow what's happening, right? So you can see I started around 10 o'clock. I probably had the light on in the room where the sensor was. Then the light goes off. You can see overnight there's nothing. It's very dark. And then in the morning, this might be, I turn on the light there, and later on in the evening, right? And during the day, it's either ambient light or there's another light on the other side of the room that might be turned on. Right, so this is, and you can see it's kind of noisy. There's kind of big jumps and lots of little bumps as well, right? So this is what real sensor data looks like. And there's a couple gaps in the data. Okay, so, and these are for the, you can kind of see from all 3 rooms. You can see they're all, it's similar, but not, they each has a little different pattern. Okay, so now I'm going to take you through kind of several of the processing steps graphically. And this is really, like I said, this is how I understood the data. It's not like you can look at a chart of numbers and make sense of it. You have to really visualize it to understand what's happening. So this is the raw data for that front room for 24 hours. So this is after I ran the smoothing phase. So this kind of removes some of the noise. And you can also see the peaks are not quite as high there, right? Because it's taking a running average, and that was a really short one. But it's definitely a little smoother there. So the next step I took from there is I ran it through a k-means clustering algorithm. And so what this does is you basically say, I have a bunch of data points. They have some values. And I give you a number of groups. In this case, I gave it 4 groups. And I want you to put those data values into the 4 groups such that the distance between the data values within a given group is minimized. So it's basically trying to group your things into 4 groups the best it can, right? And so it's an optimization problem. And it's NP complete, I believe, but they have a lot of good kind of approximation algorithms for this. And I think it's Numpy or SciPy, one of those libraries has the code to do this. No, with Scikit-learn, sorry. So Scikit-learn has this k-means clustering. So all I'm doing is I'm just giving it all these different values. So there's, maybe 100 different values on the y-axis you see here. And I'm saying group them into 4 groups. And then what I do, those groups really are just labeled arbitrarily. Then I just kind of sort them and say the group with the lowest average, that was the 0 value. The group with the next lowest average is the 1. The group with the highest is the 3, right? So then this kind of gives me a very kind of more granular view of the data, right, that I can look at. It's not quite binary yet, but it's, what is it, quadary, I guess, data, right? And so then the next thing is to figure out, so I did this for each of the rooms. And then the next thing is to figure out, well, when is the light on or off, right? And you kind of hear, if I wanted to be really fancy, and maybe this is a future thing, I would have like some light sensor outside to measure how much light's coming from outside, subtract that out and all that. But I wasn't, I would just want to keep it fairly simple. So what I do is just look at the data, and knowing what I know about the room, I'm going to say the 0 level means the light's off. Anything 1 or higher, I'm going to treat as the light being on. And so that was the same for, I think, the dining room. The back room had more ambient light. So I said if it was 2 or higher, that meant the light was on. Anything level 1 was probably sunlight coming through the curtains. So now you can see I went from there, and then I go to here, and that's basically the times when the light came on, right? Or my inference of when I think it came on. So you can see it was on at night, a short time there, a longer time there, a short time there, right? So one thing you can notice already is it's not like it's on consistently for the same amount of time. Sometimes it's longer, sometimes it's really short. Okay, so now let me talk about hidden Markov models. So I wanted to find some way now to take this data and be able to train something to be able to generate similar values. And there's a lot of machine learning tools out there to try this. And I tried some other algorithms, and I have a backup slide if you want more details on things I tried. But I kind of ran into sort of two problems with this. One is kind of one of the challenges with machine learning is figuring out you have to kind of massage the data to create what's called the features that are what the actual data that's relevant for training the machine learning algorithm. So it was tricky to figure out what that was, and you don't get a lot of feedback from the algorithm on what's going wrong. And I did find like decision trees actually lets you visualize what you're doing, which was pretty nice. But in general, it's a challenge, and sometimes I would get predictions of the lights off all the time, or it would oscillate wildly, which is not good. You don't want it every minute on and off, on and off. So, but I think ultimately the challenge I had with kind of using some of these other algorithms was that what's really important, I had maybe 25,000 samples, which is probably considered a small but okay sample group for most machine learning algorithms. But in reality, I may have 25,000 samples, but really what matters is not the samples, but where you have a transition from on or off. Because that's all that's relevant is like, how long was the light, other than the outside data, like what time it was and, other kinds of things you want to incorporate into the algorithm. But what's important is how long is, for the prediction, is how long was the light on, how long was it off, and when did that happen? And there was probably only, over those 3 weeks, there was probably only a couple hundred of those events, right? Because I'm not on and off on the switch all the time. So because of that, it's not, I don't think there's enough data for most machine learning algorithms to train it. And so one of my future work things is to kind of go try to run it for a longer time period and gather more data and see if I can do a better job with some of these other algorithms. So what I ended up with, and you can still put it under machine learning, I think, and use a very similar model. It's called Hidden Markov Models. So a Markov process is, you can think of it as a state machine where there's a probability on the transitions on which state you're going to next. And it's independent of the history of how it got there. All that matters is what state you're in currently. So here's a little example I took out of the Wikipedia page. And so they have like a state machine that has sunny and it has rainy. So if you're in the sunny state, you have a 90% chance of it being sunny tomorrow. But you have a 10% chance of rainy. If you're in the rainy state, you have 50% chance either way. So if it was sunny 5 days in a row and I'm in the sunny state, the fact that it was sunny 5 days in a row has no impact on what state I'm going to next. It's really just the probabilities. So there's a lot of things like you see Markov models, they do fun things like they take a bunch of research papers, they read them into a Markov model, and then they generate new research papers. And they submit them to conferences and get them accepted, believe it or not. Yeah, this was a whole thing that some guys at MIT did. And so you can get some, it won't really make sense if you read it in detail, but you can get some text using Markov models that looks pretty good, right? And yes? So why did I use Hmmlearn instead of Sklearn? Well, I think, so the hidden Markov model part was part of Sklearn and they broke it off. So now it's a separate library. So I think it was originally part of it, now it's separate. And it has a very similar API though as the rest of the Sklearn algorithm. So I was able, since I had started with Sklearn with the other machine learning algorithms, it's fairly simple to switch it over to this. Anyway, so a hidden Markov model is a Markov model where the states are hidden. It's a black box. And so from a machine learning context, what you're trying to do is you're given a sequence of what they call emissions, which are just the outputs. And given this sequence, you want to, and you pick a number of states, then you want to basically use some optimization algorithms to infer what the state machine looks like. What are the transitions? What are the probabilities? So that's what the Hmmlearn library will do for you. Yes?
So are you a state
Well, so I don't have any control over what meaning it assigns to the states. The learning algorithm is sort of a black box. It doesn't have any. And you could probably write some custom code to infer this, right? But the general hidden Markov model learning, it doesn't have any special meaning for those states, and it's inferring what those are. Now, when I picked the number of states I wanted to use, so you have to tell it how many states you want in your state machine. What I did is I kind of looked at the data and I said, well, I need at least 2 states. I need an on state and an off state, right? But I also have things where you notice that it's on for a short amount of time or a longer amount of time. So to handle that, what I want to do is I want to have at least, additional states to cover those cases. So I estimated like 5 states should be good enough, and it seemed to work.
How did you guarantee that the Markovian assumption, which is mostly the one that you have expressed fully,
Right.
is validated?
Well, I guess there's no way to really guarantee. Again, I'm just trying to get predictions of something. This is not really a true classification or regression problem, right? I'm trying to build a random sequence that looks similar to the original, right? And I guess I have no way of saying, there's a lot of physical processes that tend to follow this. But, and from looking at the data, my assumption is that if the light is off, right, there's some random process that's going to determine when it turns on. And exactly, and in general, it probably depends somewhat on how long it's been on, but the full sequence that happened before is probably not important. Then again, that's just my assumption. But given that I got reasonably good results, I'm going to say it was good enough. All right. Yeah. Uh-huh. Whether that holds. Okay. So. Uh-huh. Okay, well, that's good. I'll look that up then, and that's good to know. Anyway, so like I said, the goal is we have a bunch of data, and we're going to pass it to this algorithm, and it's going to come up with a state machine for us, and then we can use that to generate emissions in the future that are basically then future samples. And again, I'm using this Hmmlearn library. So one of the problems with this, as opposed to some of the other machine learning approaches, most of them I was able to, in the feature data, I would put in some concept of what time of day it is and things like that, because obviously the light pattern varies depending on the time of day. So what I did kind of to work around that issue, and and it probably also is useful for other machine learning approaches, but I kind of split the day up into different what I called zones. And so, and the logic I used to do that was based on when is sunrise and sunset for a given day, as well as certain things about like what, at night, I know, okay, we try to get the kids to bed by 9:30, even though they should be to bed hours before that. But so basically, I kind of split it up into these 4 zones. And the key thing is like there's a zone that begins at midnight and goes till sunrise. And usually there's no lights on then, right? So I want to have a separate model for that time period than I want to for the middle of the day. So what I'm going to do is, so like this shows you data from one day. This is zone 0. This is zone 1. You can see the light was on twice then. Zone 2 once in zone 3, right? So I'll infer a separate model then for each zone. So this is kind of the process then. First of all, I take these samples that I've gathered, and I build a list of subsequences. So I first of all split them by zone, and so I have a sequence that here's the data from this day in this zone. And then whenever there's a gap in the data, I need to make that a separate subsequence. And then you can pass to the training algorithm. You can pass a bunch of sequences, and it'll take advantage of all of those things. And I guessed a number of states. I pass it to this thing. There's a magic function you call or method you call on it, and then it will basically infer a hidden Markov model for you. And so then what I want to do, if I want to do predictions and want to generate more data, what I do is for a given day, I figure out what the zones are for that day because they vary depending on sunrise, sunset. And then I run this hidden Markov model for each zone for the number of samples for however long. So if my zone was 2 hours long, then I have 120 samples that I need. So I say, give me 120 samples. So it gives me a time sequence of 120. Then I just attach timestamps to those, and then I have a bunch. Then I just splice together the 4 zones of the day, and I have all the predictions for the day. And then the key thing after that is to actually look at the data to see if it makes sense. So this is like some predicted data. Here, this is over a week. You can see what it looks like over a week, and this is one day. So you can see during the day, in the middle of the night until the morning, it's not on. Then it's on a couple times and longer times, and then some shorter times later at night. And it seems reasonable to me. And each day in each room then is going to be slightly different. And again, it's not all off. It's not some regular pattern, and it's not going oscillating crazily. So, okay, now replaying the lights. So to replay the lights, again, I'm using my Raspberry Pi and this Phillips Hue setup. So it's fairly simple. So there's this Hue library that you can get from PyPy, the Python package index. And I can use the code that I had already created in the analysis phase for basically figuring out what the time zone is. And for that, actually, all I did is I found some chart online, and I just put that basically gives you the sunrise, sunset for the whole year, and I just stuck that in the code. There is some library to do it in Python, but I think it's basically any body in the solar system, it'll tell you the sunrise. You give it the moon, and this location on the moon will tell you sunrise, sunset. And I didn't want to figure out how that library works, so I just kind of hard-coded the logic for 2016. Anyway, so I'm reusing that logic. And so this is a pseudocode then of how I do it. So I basically, one of the things I learned from experience, you're going on a road trip, you're running late, you want to beat the traffic. You don't want to be fooling with this thing, right? So first thing I do is when you start the program up, it goes and turns on the lights in each of the rooms in sequence and does like 5 seconds on, 5 seconds off for a minute. That way you know that the bridge is working, the light's working, everything is kind of working there. And you can kind of trust that it'll do stuff the rest of the time. So then what it does is it goes in this loop and it predicts what are the values going to be for the rest of the day using that same thing that I did in the offline analysis. So split, I know what time it is now. I know how many samples I need to the end of the day, what zones they're in. I use the right hidden Markov models to then build these samples for the rest of the day. So from there then, to make it a little more convenient for controlling it, what I do is I actually figure out from those samples, I go, where are the transitions happening? Because that's really all I care about. So then I throw out everything else and just keep the transitions. So I have basically then a time-sorted sequence of events of on or off for each light, and then I just merge them all together. And once they're merged, then I can basically say, pull the event off the head of the list, sleep until that event time happens. So I have a little function to say, okay, what time is it now? How long do I need to sleep? Sleep until that happens, then get the control message and send it off to the lights, and then pull the next event and go back to sleep again. So that's the logic for the controller then. And then when this loop is done for that day, you need to wait until the next day. If you don't, then you come home and you find you have an assert failure in your code. So you got to wait till midnight. There were a couple edge cases I had about, depending on exactly when the last light went off and midnight and things. But then you wait till the next day and you run the same logic again. And that's like, I don't know, the whole file, including comments, is like 200 lines. Okay, so that's pretty much it. So first of all, some acknowledgements. So Rupak Majumdar, he was my PhD advisor back in the day, and he's now at the Max Planck Institute for Software Systems. And so he and I kind of did this AntEvents and, are doing a few other things with that. And Zining Ching was an intern working for Rupak over the summer, and she was the first person to actually use the code and actually was able to get it to work, surprisingly. And she did some cool stuff where she took the Esp8266 and some accelerometers, basically wore those around, gathered data using AntEvents and Micropython, and then put it through a machine learning algorithm to try to figure out if you're walking or running or what. So that was pretty cool. And one of the things that we found is that the sample loop, we can sample maybe 5 times a second. If you try to go much more than that, they can't really handle that. Then you probably have to go down to C. And then Dimitri, he's a frequent attendee of BayPiggies. I had been talking to at one of their meetings about this, and he offered to have coffee with me and kind of explain to me some of these machine learning techniques. So thank you. And so some lessons learned. One thing is I think an end-to-end project is a great way to really learn an area, right? And it was definitely a lot more work than I thought it would be to do all this stuff. And I went down a couple rat holes, right? And sometimes you have to know when to get out of the rat hole and when to cut corners, you know. So maybe I had envisioned some more grand ideas. But, you know, I got something working end to end, and I really learned a lot about it, different areas. And I've done some other stuff with IoT in the meantime in my day job. But I think, you know, I can talk a lot more intelligently about IoT now. And then, you know, applying machine learning, this is really my first experience with machine learning. And you can see it's kind of figuring out how to train the algorithms and what data you need and which one to pick. At least from my perspective, it's still very much a art rather than a science, right? And I'm sure that as you know, if you do it day in, day out, then you kind of get the gut feeling of what to do. But you know, one of the things is like you go read this Scikit-learn thing and it's like, oh, I want to classify these pictures of flower petals. But you read that and then that doesn't really get you to the point of really understanding how to apply it. I think you have to kind of tackle a new problem to really get how you apply this thing in the real world. And another thing is for like IoT systems, I think visualization is really the key to understanding your data. Because there's no way if you just see a bunch of data on a spreadsheet or whatever, or through some program analysis that you can really understand it. You have to visualize it to see if it looks good. And finally, Python ecosystem was great for both kind of the runtime piece as well as the data analysis piece. And it was useful to be able to use the same code in both places. Okay, so future work. So at some point, if I get the energy, I'll hook the sensors all back up again, maybe gather light for a while, and see if I can get enough data that I can really push some of these machine learning algorithms and get something more interesting out of them. We're also working on integrating AntEvents with some visualization tools. So we're looking at Bokeh. It's a Python server and client framework for doing visualizations. And one of the key things we want to get, well, two things we want to accomplish. One is Bokeh already has a thing where if you see time series data, you can kind of zoom in and zoom out. And that's very helpful because in Jupyter today, most of the basic graphing things, you're kind of doing that in code, and that's painful. So being able to zoom in and zoom out and kind of look at different things. Yes?
There's a new thing called Caravelle.
Caravelle?
C-A-R-A-V-E-L. They presented in Python.
Oh,
The same guy who designed Tableau.
oh,
It's more powerful.
okay, So maybe we'll have to look at that too, Caravelle. And anyway, but I think, you know, so I think there's some interesting things to look at. The other thing that'll be cool is we want to do is as new data comes in, basically add it to the visualization, right, in real time. And then finally, kind of one of the questions we're trying to answer more from a research perspective is what are the right abstractions if you're doing analytics over this data? It's different from most of the analytics you see done in the industry today is about, if it's time series data, is about, you know, stocks or click streams or things like that. And so, but I think this IoT data is different. It's noisy, it has gaps, and you know, it may be coming at a very high frequency. So what do you do to make sense of that data? That's kind of a bigger question that I'm trying to get a handle on. So, and so I will try to show you a demo. I think, let's see how this goes, to just show you that the thing actually works. Somewhere here. Okay, so if I do, there you can see, hopefully you can read that. That's a Micropython prompt there. And let's see, somewhere. Okay, Emacs. So what I'll first do, okay. So when I have to hit, let me see. it wants a special to do the Python copy and paste. Okay, Control E. Okay. So there I just grabbed a sample. So if I just type now in the Python prompt, every time I type that now, I have a sensor, I can sample the value, right? So if let's see. If I put my hand over it, it should give me a lower value, right? Cool. So now what I'm going to do is kind of put it in a loop. And I'm going to create this kind of downstream thing, which will just print out the value of the event. So I think it was Control E, Control D. Okay. Already I did something wrong.
On the paste, you add head instead of head.
Oh, okay. That's not good. So then we'll do. How's that? Okay, then we can try it again. Yeah, that's why it's a live demo, right? You know I'm not faking it. Okay, so now it's Control E. This copy paste thing is not the most, okay. So now it's going to be running in a loop in the AntEvents scheduler, and every, I don't know what I said, 2 seconds it's gathering a sensor value, and the other number is a timestamp. That was another challenge I found. I think there was actually a bug in the code in Micropython. I need to actually file a bug report because they have some problems where the real-time clock on that is not, it's only like 16 bits. So it wraps. So kind of dealing with that in the scheduler was a little tricky. So now if I put my hand over it, yeah, so now it goes down for a while, right? So anyway, and well, so that's it. And let's see here, I think there's be one more. Okay. Okay, so that's it. Any questions? Yes?
2 questions. One, was when you go out on vacation, did anyone broke into your house?
No.
Second question, did you see, how was your electricity bill compared to when you were not automated?
I didn't look into that. I mean, that's actually one of the other ideas we had for this app is, and that, thank you for reminding me to repeat the question. He was like, how did my electricity bill vary, right? So I didn't, in terms of like turning on and off these lights when I'm on vacation, I don't think it makes a big difference because it's just one weekend. And again, the computer power that I'm running is very small too, right? Because these things can run off of batteries or whatever. But I think there's another question that actually you just reminded me of, which I think you can use this to gather data about usage of the lights in the house. So it would be another cool app to build. Maybe this is a future work thing, is to monitor the light levels, figure out when lights were turned on and off, and build some kind of charts that say, okay, what do these things look like? And you could also, if you want to get fancier, you could probably have presence detectors to know when people are in the room. And then I can tell my kids they need to turn off the lights more, right? It's the main goal of that. And also, if anyone has a longer question, you can take up. We have microphones here.
How long does the battery last?
Oh, how long does the battery? I don't know, because I've been mostly running them off of the USB. So I'm assuming it runs a couple days, but I'm not really sure. I mean, one of the problems with this, well, the good thing, because it's Bluetooth, it has a lot of range, but Bluetooth is pretty power hungry not Bluetooth, sorry. This Wi-Fi, it has a lot of range, but it's pretty power hungry compared to Bluetooth, I know that. And then you could probably do a calculation to figure out how long the battery lasts. I haven't bothered doing that though. Yes?
Do you have an estimate of price for the project?
The price?
Yeah, like how expensive the bulb, this microphone.
Okay. So it's like a, So I think the Phillips is somewhere like 100 to 150 bucks that's a set with 2 bulbs and a bridge. So
$70 the hour for starter kit.
yeah, and so they have that at Amazon and I think even at Lowe's and places. Then the Raspberry Pi, I don't know, they're pretty cheap. And those boards, the Esp8266, they're $16.
$7 an hour.
So, it's maybe, if you exclude the lighting part, it's maybe $100, $150. Right, obviously I bought more, like you saw those tools, I didn't have a soldering iron, I don't know, that was maybe 30 bucks. But now I can reuse those for other projects, I guess.
You can get a starter kit for $70 at Best Buy.
Oh, cool. That's a good question. Oh, I don't want to know. So the question was, what is the calendar time it took to develop? I mean, in terms of elapsed time, I think we started in maybe April. My startup died in February, so I had some free time. We started in April working on this project. I mean, I was working full time then. And I spent a couple weeks over in Germany with my former advisor kind of working on we basically have a little hackathon to kind of hack out what are the abstractions we wanted in AntEvents. And then it was kind of like an evening and weekend project here and there. And I really finished it, I would say like end of July. And then didn't touch it really until I had to prepare for this talk and try to remember what I did. And then I do actually use it. I mean, we go out of town, usually I'll turn this thing on and have it fired up, and we haven't been broken into, but I guess that's not, very, I don't want to say anything, I don't want to jinx myself, but yes?
So is your next step to set it up so you can turn it on with your phone? When you forget to turn it on?
Oh, that would be a good thing, but of course then you're talking about cloud services and things like that, and you have security issues, but that would be a cool thing to do.
Do you have a plan to hook up a automated machine gun?
No, but actually a couple years ago, I mean, if you the coolest Python talk I ever saw was at PyCon. I don't know, it was when it was in Santa Clara a number of years back.
Is that the squirrel gun?
Yeah, so this guy had a gun, I don't know, I think it was a squirt gun or something. He was using machine vision to shoot squirrels off his bird feeder.
With water.
With water.
Water.
Yeah. So it's been done before.
You can club it with a PIR, and once the PIR detects some motion,
Right.
then you can live stream what's happening.
Right, but the tricky part, I think, of the project, if I remember correctly, is you need to not only detect motion, but distinguish between squirrels and birds, right? So, yes?
So having worked with sort of all levels of the Internet of Things stack, where do you see the strengths of this? Where do you see the challenges? What do you see as the opportunities?
Okay.
The hardware, the software, the analysis portion of it?
Well, I don't know, strengths, that's a hard question to answer. Well, I mean, well, I think one of the things like compared to before, from what I tell, I think one thing that's changing in the industry that's good is there's more standard things out there. So I heard someone told me that like GE was actually using Raspberry Pis for doing analytics, and the thing is when you have it's all open source, it's all standard, because it used to be before you have some electrical engineers that don't know a lot about programming, and they go get this SDK and this thing with this weird IDE from a hardware company, right? And then they have to kind of figure it's like this arcane black art. So I think now the nice thing is it's all changing, and we're now seeing a lot of open source and a lot of more open things that people are actually using them for things. So I think that's a great evolution. I think the challenge is now, so I was on the bleeding edge of this Micropython thing because they had a Kickstarter to port it to the ESP8266. So I was using their beta versions, and it was a little flaky at first, and it's definitely gotten better. But I would say, so that was a challenge. Another thing would be just in general kind of how do you manage an application stack, and you don't have all those things you have in the cloud like containers and deployment engines, and right, you don't necessarily want all that complexity, but there's no real way to kind of manage your thing and make it reproducible. So I think that's an opportunity for future growth. Yes?
Show charts of recordings for your data collection.
Yeah.
When you were out on vacation, the replay that it did, do you have charts for that?
No.
Sure that it replayed in a more non-predictable way or it matched very much with the reality of the event.
So I kind of know from two things. I mean, I could build charts. It's just I would have to capture the data and then build up the chart. I never bothered. So two reasons. One is because I did the replay. I did the replay in Jupyter Notebook, right? So by doing that, then I had a pretty high confidence of what the data is going to look like when I run it. The second thing is in that one loop it has in the program, the first thing it does for each day is it prints out what it's going to do. So I can look at that and look at what it's going to be doing and see if it makes sense. And then it prints a log file of all the events it does. So I can kind of look at the log file and say, yeah, did it, well, first of all, is it still running when I come home? And the second thing is, did the events look reasonable? And so that's really kind of how I did it. I could visualize that, but there aren't enough events that it kind of, I felt justified that I needed.
I asked is, when you are recording it, you had different humans. When you are playing it, it's either on or off.
Right.
So how does it record it when you are actually playing?
Well, so I'm just, now if you want to get fancy, so the question was kind of, the data you're gathering is kind of different levels, and now I'm going to on or off, right? So part of my analysis was to try to infer when it's on or off from that noisy data, right? And of course, I don't really have to be perfect. And like I said, if you want to be fancy, you could subtract out the ambient light or something like that. Or you could have a sensor to know when someone turned on the light, right? But that's a lot more work to kind of set that up. So I just really care about turning the light on or off from the, I don't really care about the exact lighting level in the room. You could do, this thing has a dimmer in it, so I could actually control if I wanted the lighting level to be a particular level. But I didn't really see, particularly if no one's there to see it, I just care about what it looks like from the outside, really, right? The guy in the back.
Which one is harder to get yourself around hardware and how to look it up, data or machine learning algorithms? Or in other words, if someone knows one of them or the other, which one would?
Well, I would say the machine learning is definitely harder, right? If you want to, well, maybe it's because I did have a background in the hardware, even though I hadn't done it. But the hardware, like again, there's only like 4 wire connections there. So it's not that bad. And you don't need to have fancy equipment. The machine learning, I think, is sort of like, well, that's like an ever expanding thing, right? You can, if there's sort of like kind of knowing it at the level I do, which is knowing what the process is and knowing kind of what some of these algorithms doing. Then there's really understanding the math behind the algorithms and improving those algorithms, right? And I'm certainly not at that level. Yeah. Well, it wasn't technically hard. It's kind of like if you've done stuff on any server to fool around with Linux. It's one of those things like where things might not work the first time, then you go, oh, why did this? Like when I was trying to set up I had to run the machine learning code on the Raspberry Pi. And so I said, well, I could get the pre-compiled packages, but there was some reason why I didn't want to. I don't remember why now. So I said, okay, I'm going to have it do the install through pip, which is the Python install thing, and it's going to install everything from source. Well, then it decides that it needs a Fortran compiler. And that's because the SciPy thing is actually using Fortran libraries. So that's when I decided I'm going to go back and find some way to use pre-compiled things. But those things, you might waste, then you waste an hour on that process, right? But that's not like hard. I won't say it's intellectually hard. It's one of those things you just kind of work around it and keep on playing with it until you get the right thing. Yes. Yeah.
So did you see variation? Because once you train the model,
Right.
once you give it an input, the input doesn't change. It's just a series of time. So you should see the same observations, right? Same predictions.
Well, it's two things. One is it is a random process, right? So,
Because
right. So the question, let me repeat the question. The question was, why isn't it always doing the same thing? So since it's a Markov process, it's going to be random. And the second thing is, it's also predicated by when the exact time it's in each phase every day depends on the sunrise, sunset for that day. So based on that, then it's going to be a little different every day as well, right? So I'm hoping, I should try to run it and make sure, but because I captured all this data when the days were much longer, right, in July. So if I run it now, it should hopefully do the right thing. Yes?
I realized you said doing a set schedule. How would you do this differently if you wanted to say take it whether it's sunny that day or not, or whether it's cloudy or rainy? Use a different machine learning model? Would you tweak the way you're?
That's a good question. I think you could do a couple things, right? So if you, in a more general machine learning model, what I would do is, and I kind of thought about doing this and just never got around to it, stick a sensor outside or kind of, where it's only getting outdoor light, not any indoor light, and use that as one of the data values coming in. And then if you're doing kind of a more,
Or assume that the light sensor is the thing that triggers you to turn on the light in the first place.
what do you mean,
I mean, the reason you turn on the light in a room is because the light is low and you need light. So it seems like you're capturing the light data, that the impetus for turning on the light.
well, but I guess the thing is, the light could be coming from a couple of things, right? It could be the ambient light. It depends on if the shade is open or closed. Right, so depending on that and the light level outside, as well as whatever lights in the room happen to be on. So most of these rooms have multiple lights, and if my daughter comes through and turns on every light in the whole area, then that's going to give me a different reading then, right? But one of the general ideas that I had originally that I never got to was to capture the light level outside, because knowing that you may impact, right? If it's a really cloudy day, you may turn on the light more, right? And then if you fed it into some black box machine learning algorithm, in theory, it should be able to use that as one of the things. But I think the challenge is you need to have enough days and enough data for it to really make the right inferences.
And it's hard to have a cloudy day and sunny day.
Well, we had one today. But yeah,
Lights on all day.
Thank you.
sure. Any other questions? Yes?
Did you account for weekday versus weekend variations in light?
No, I probably should have. Well, the one thing is it was over the summer and my son was out of town most of the time. We didn't really have the whole pattern of, I guess I went into work and stuff, but it wasn't as pronounced a pattern as it would be now during the school year. But actually that's something we probably should also take into account is what day of the week as well. And certainly if you were, again, building a machine learning algorithm and feeding it all the right feature data, one of the things you want to feed it is the day of the week, I think. Anything else? Okay, thanks a lot for coming. Oops. What? Oh, and there's more pizza in the back. I'm supposed to tell you that.
Feel free to take as much home as you want. We have to throw it away otherwise.
Oh my God, no. Seriously?
Yeah.
What? Yeah.